All right, so we are continuing on in our discussion of the gas laws. From Unit 13, we are working on objectives 4 and 5, where it says describe how pressure, temperature, and volume of a gas may vary if one quantity has changed. And we're going to now use the combined gas law to quantitatively predict changes in pressure, temperature, and volume of a gas. All right, so far we've done some mental math with where only 2 variables change. Today we are going to look at when all 3 variables change. We're going to start out with this idea of mental math that we don't need a calculator, but then we're going to investigate maybe sometimes we will need a calculator. Okay, so our first problems that we're going to work through says that initially a gas is at a pressure of 3 atmospheres. So there's our initial pressure. Our initial volume of the gas is 12 liters and an initial temperature of 300 Kelvin. So the question is, what would the temperature be if the volume was increased to 24 liters and the pressure was decreased to 1 atmosphere? So let's first take a look at if the volume's going to be increased to 24 liters. So from 12 liters up to 24 liters, that is an increase in a volume by a factor of 2. Okay, what would that alone do to the temperature? That alone would also increase the temperature by a factor of 2. So if the temperature was originally 300 Kelvin, we would now have a temperature doubled to 600 Kelvin. But we can't stop here because there's also an effect from the pressure. So we have to temporarily say, okay, the temperature is going to go to 600 Kelvin, but now let's see. The pressure is decreased to 1 atmosphere from 3 atmospheres. So the pressure is decreased by a factor of 3. Right? We took 3, we divided it by 3, by the factor of 3, and we now have this 1 atmosphere. What is that going to do to the temperature? Well, if pressure decreases, temperature will also decrease by the same factor. So we have to take that 600 Kelvin, divide it by 3, and we will then get a pressure or temperature of 200 Kelvin being the final temperature. So let's take a look at the second scenario, see if we can work through this one. What would the volume be if the temperature was decreased to 75 Kelvin and the pressure were decreased to 1.5 atmospheres? So let's take a look at that. First thing that's changing is the temperature. The temperature is decreasing down to 75 Kelvin. Okay. Originally the temperature was at 300 Kelvin, going back to the very initial conditions, 300 Kelvin, down to 75 Kelvin. That's decreasing by a factor of 4. Okay, so the temperature went down by a factor of 4. So what would that do to the volume? If temperature goes down, the volume would also go down by a factor of 4. So the volume, which was originally at 12 liters, if it's going to go down by a factor of 4, it would now give us a volume of 3 liters. But we can't stop there because the pressure is also changing. So the pressure is decreased down to 1.5 atmospheres from 3 atmospheres. So the pressure is decreasing by a factor of 2. So that means what's going to happen to the volume? Well, pressure goes down, volume goes up by a factor of 2. Right? So we will then take this volume of 3 liters and double it to give us a final volume of 6 liters. Okay, so go ahead and try that third scenario, which says that what would the pressure be if the temperature were increased to 600 Kelvin and the volume was tripled? Okay, try that one on your own. Bring your answer to class. What you can see here is that clearly mental math is sometimes useful, but sometimes we are going to have to be dependent on a calculator because you know what, these numbers are not always going to be so nice and round for us. Right? So all of this comes together into what we call the combined gas law. Okay, so we're now really studying the quantitative relationships. What happens to these quantities of pressure, volume, and temperature when either pressure, temperature, and or volume are changing? So we have here this equation, P1 times V1 over T1 equals P2 times V2 over T2. Of course, P is pressure, V is volume, and T is temperature. So anything with a 1 represents the initial conditions, and anything with the 2 represents the new conditions, right? So here's the thing, there's 6 variables here. You're going to be plugging in, if all 3 variables are changing, you would be plugging in 5 numbers and solving for the 6th. You know, this is how you will work this equation. Now, what's kind of clever about this equation, well, first of all, let's give this a name. When I say use the combined gas law, this is the one. Okay, so here's the thing, this combined gas law. If pressure is remaining constant, cover up the p's. Okay, cover up the p's. And what you are left with, or take the p's out of the equation. So if pressure is constant, remove P1 and P2 from this equation. And what are you left with? You're left with V1 over T1 is equal to V2 over T2. And that's the equation that you would use. If temperature remains constant, take out the t's out of this equation, and what you have is P1 times V1 equals P2 times V2. If volume is remaining constant, take volume, the V1 and the V2 out of this equation, and what you're left with is the equation that you would use, P1 over T1 is equal to P2 over V2. So this combined gas law, this one equation, covers Boyle's law, it covers Charles's law, and it covers Gay-Lussac's law. Now, a couple things to keep in mind. P1 and P2 must have matching units. It doesn't matter if the pressure units are both for P1 and P2. If they're both millimeters of mercury, that's fine. If they're both atmospheres, that's fine. If they're both kilopascals, that's fine. But what you cannot have is a pressure unit for the initial conditions in atmospheres and a P2 pressure unit in millimeters of mercury. The pressure units must match, or else they don't cancel, and then the math doesn't work. So I don't care which pressure unit you use, so long as they match. Same for volume. The volume units must have matching units. Either they both have to be in liters or they both have to be in milliliters. It does not matter so long as they are the same. The temperature units must also match, but it does matter which unit you use, and that unit, of course, has to be Kelvin. Okay, you must have matching Kelvin units for both temperature. If they're both in Celsius, this equation, your math will not come out properly, and you'll have a wrong answer. So make sure temperatures are in Kelvin, and that's true for both T1 and T2. Okay, so now what we're going to do is we are going to manipulate this equation, starting with P1 V1 over T1 is equal to P2 V2 over T2. Want to make sure that everyone knows how to manipulate these equations. Solving for P2, remember these are cross multiplications, right? There's an equal sign in the middle. So if I told you to solve this for P2, what you would do, cross multiply. So what you have here is P1 times V1 times T2 is equal to P2 times V2 times T1. But we're trying to solve for P2. We've got to get P2 all by itself, so we would divide both sides by V2 and T1. So P2 would therefore be equal to P1 times V1 times T2 divided by V2 times T1. Okay. Try solving for V2. You're starting out with the same thing. P1 times V1 times T2 is equal to P2 times V2 times T1. And since we're trying to solve for V2, we would divide both sides by P2 and T1. And now it's just a matter of plugging those numbers in, having solved for the V2. All right, try solving for the rest of those on your own. Actually, let's do this one together because T2 is in the denominator. We'll do this one final one together. what we have is P1 times V1 times T2 is equal to P2 times V2 times T1. Solving for T2, we would have to divide both sides by P1 and V1. And there you have it. T2 is equal to P2 times V2 times T1 divided by P1 times V1. Okay. So please take a moment to finish manipulating the remaining three variables. Okay. Also keep in mind there's some equations that I believe are written on your handout. These are just reference materials that if you have forgotten what all these are, they are there for your convenience. All right, now what we're going to do is work with some problems that have a little more quantitative aspect to them, not as easily done as mental math. So what we're going to do is we'll set up this chart. What we have is column 1 and column 2. That's for the initial conditions and the new conditions for pressure, volume, and temperature. So when you read through the problem, it says a gas whose temperature remains constant has a volume of 2.32 liters at 1.09 atmospheres. What will its new volume be if the pressure is changed to 0.995 atmospheres? Okay, so what we see here is the temperature is remaining constant, so I'm going to put dashes through those. It has a volume of 2.32 liters to start, and its initial pressure is 1.09 atmospheres. What will its new volume be? So that is going to be our x if the pressure is changed to 0.995 atmospheres. Okay, so in this case what we are going to do is, if we know that we're starting with this equation, we know temperature is going to remain constant, so we will basically ignore the temperatures here, and we are really just doing this equation. P1 times V1 equals P2 times V2. We want to solve for V2, which means I have to divide both sides of this equation by P2. And now we know that V2 is the pressure, the initial pressure times the initial volume divided by the new pressure. So now it's just a matter of plugging in your numbers. 1.09 atmospheres times, that's the first pressure, the first volume is 2.32 liters, and we're going to divide that by the new pressure of 0.995 atmospheres. Atmospheres cancel. When you plug this into your calculator, you get to three significant figures, 2.54 liters. All right, let's take a look at example number 2. A sample of a gas occupies 4.00 liters at 300 degrees Celsius. What temperature in degrees Celsius would be necessary to cut the volume to 3.50 liters? Assume pressure remains constant. So since pressure is constant, I'm going to put dashes through both P1 and P2. And we're going to work on identifying our initial volume. Our V1 is 4.00 liters. Our new volume will be 3.50 liters. Now the temperature initially is at 300 degrees Celsius, but we can't use degrees Celsius, so we're going to need to add 273 to get our Kelvin temperature. This, of course, adds up to 573 Kelvin. That's our initial temperature, and our T2 is what we are trying to find as our X. So if we start with the P1 V1 over T1 equals P2 V2 over T2, now we know that pressure is going to remain constant, so if we take pressure out of this equation, we are left with V1 over T1 is equal to V2 over T2. And since we are trying to solve for T2, if we cross multiply, we have V1 times T2 is equal to T1 times V2. And since it's T2 we're trying to solve for, we would need to divide both sides by V1. So now that we know what equation we're working with, we can just substitute in. T1 is 573. V2 is 3.50 liters. And divided by V1 of 4.00 liters, liters cancel. And when you put this all into your calculator, you get 501 Kelvin. Now, that seems like that should be the answer, but if you read the problem carefully, it said that we needed to report our answer in degrees Celsius. So, of course, what we need to do is convert back to Celsius using the K equals C plus 273. And what we know is 501 Kelvin is equal to C plus 273. We'll need to subtract 273 from both sides. And when we do that, 501 minus 273 works out to 228 degrees Celsius. So that's how you work through that particular problem. Let's take a look at problem number 3. We have a fixed volume of a gas. It exerts a pressure of 1.25 atmospheres at 0 degrees Celsius. What would be the pressure if the gas is heated to 50 degrees Celsius? Well, a fixed volume means that volume will not change, so that's what's going to be constant. Our initial pressure is 1.25 atmospheres. Our P2 is what we're trying to solve for. And now we have two temperatures in Celsius that we need to first convert to Kelvin. Well, 0 degrees Celsius is 273 Kelvin. 50 degrees Celsius, if we add 273, that works out to 323 Kelvin. So our initial temperature is 273 Kelvin, and our new temperature is 323. So if we start with the full equation, P1 V1 over T1, we know that volume is going to stay constant. So we'll take volume out of the equation. That leaves us with P1 over T1 equals P. Oh, I made a mistake here. Of course, these should be 2's. P1 over T1 is equal to P2 over T2. When we cross multiply, we have P1 times T2 is equal to T1 times P2. We are trying to solve for P2, so that means we're going to need to divide both sides of the equation by T1. And there we have our equation all ready to be plugged in. P1 we know is 1.25 atmospheres. T1, or I'm sorry, we're going to multiply that by T2, which is 323 K. And we're going to divide by T1, which is 273 K. When you plug that all into your calculator, that should work out to 1.48 atmospheres. And that, my friends, is the final answer for problem number 3. Now notice in each of these problems we had one variable staying constant, and we had one problem where volume stayed constant, a second problem where temperature stayed constant, and a third problem where pressure stayed constant. In our final example for this video lecture, we're going to see that none of the variables remain constant. We have 2.00 liters of a gas. It's collected at 25 degrees Celsius and 745 millimeters of mercury. What is the volume at standard temperature and pressure? Alright, so what do we have? Our initial conditions. The 2.00 liters is our, not our initial temperature, is our initial volume. It is collected at 25 degrees Celsius. That's our initial temperature. But we have to first convert this to Kelvin. So adding 273 to our Celsius temperature, we get 298 Kelvin. Our initial pressure is 745.0 millimeters of mercury. The question says, what is the volume at standard temperature and pressure? So our V2 is going to be our X, And now we need to remember what standard temperature and standard pressure are. Now remember, we need to make sure that the temperature units match. So standard temperature is 0 degrees Celsius, which of course is 273 Kelvin. Standard pressure is 1 atmosphere, but since our initial pressure is in millimeters of mercury, we should make sure that we use the pressure for P2 that is also millimeters of mercury. Standard pressure in millimeters of mercury is 760.0 mmHg. So if we start with our problem, P1 V1 over T1 is equal to P2 V2 over T2. We're solving for V2, so let's rework this equation. P1 V1 times T2 is equal to T1 P2 V2. Dividing both sides by T1 and P2, because we're trying to solve for that V2. What you do to one side of the equation, you have to do to the other. And so there is our equation ready for plug-in. So P1 745, so 745.0 mmHg times V1, which is 2.00 liters, times our T2, which is 273 Kelvin. We're going to divide that by T1, 298 Kelvin, multiplied by P2, which is 760.0 mmHg. You can see that mmHg's cancel, Kelvins cancel, leaving you with the only unit of liters. And now be careful when you do the math here, when you're dividing by 298 and 760, make sure you are dividing by the product of those two numbers. If you've done this carefully in your calculator, and I would like you to actually try it yourself to verify that you can get the same number that I do, you should work this problem out to have 1.80 liters as the new volume. Alright, this includes this video lecture in the introduction of the combined gas law. We'll see you in the classroom where we'll get to do more practice.